Hey there, this is another edition of Kung Fu Physics where we are presently working our way through practice physics GRE problems one at a time. I have the mechanics problem for you. It's number 65 off of the 1996 exam. It looks like this. So number 65 off the 96 exam. We'll go right into it. I usually glance at the answers. In this case, I just got a whole mess of variables and or constants there. They don't really help me that much, so I just take a quick glance at what my options are and then go into reading the problem. Number 65. A man of mass little m on an initially stationary boat gets off the boat by leaping to the left in an exactly horizontal direction. Immediately after the leap, the boat of mass m is observed to be moving to the right at speed v, little v. How much work did the man do during the leap, both on his own body and on the boat? Okay, so I'm going to draw two diagrams of what's going on here. The first is going to be the guy sitting in the boat, mass m, and the guy who I'm going to draw as just a ball, because we physicists can get away with doing crap like that. He's just sitting there in the boat. Now immediately after, it says he goes to the left, so the man M goes to the left with some velocity that we don't know what it is, and it says that he kicks the boat as he jumps, and we do know the boat is moving with velocity v, little v. I think I've got that right. Yeah. Big M, little v. I'm going to label in his velocity as v prime. The problem doesn't tell us to do that, but it'll be useful. So what I want to point out in this situation here is initially everything's sitting at rest. Because everything we're taking as the same horizontal level, it doesn't say the guy jumps up or down or anything. There's no potential energies involved. So the potential energy in this situation would be 0 or whatever. The potential energy in this situation would be 0. But the kinetic energies have certainly changed. Here the kinetic energies of both the boat and the man are 0. Everything's at rest, right? But down here we have motion. We have kinetic energy in both the boat and the man. So you may ask yourself, well, what happened? If energy is conserved, how is there no kinetic energy here, yet kinetic energy here? Well, something has done work on the system between here and there. And what has done work? Well, the man did work. That's what's described in the problem. The man did work. How did he do work? Well, he used his legs, he coiled like a spring or whatever and jumped off the boat, pushed off. And so he's burning calories. Whatever he ate for breakfast today is being burnt up. He's expending energy and he is doing work, and that's what's asked for in the problem. So basically we need to find out what the difference is. If the kinetic energy initial is 0, what is the energy in this final situation? Equals what? Because that, we know, all came from the man doing the work. And so that's really what's being asked here. How much kinetic energy is in the final situation? And so to get the kinetic energy in the final situation, we just need the kinetic energy of both things. The boat is easy. We get that first. 1/2 m little v, big M little v squared. And then we're going to add in 1/2 little m, the kinetic energy of the man, times v prime squared. This is where our problem comes in, because we don't have v prime squared. We don't know what that is in terms of anything else, of the other variables. But we can get it from conservation of momentum. Just looking at this and understanding the problem, you realize that the momentum is going to be conserved as well. Right in that instant after he jumps off, the momentum going in either direction is going to be equal. In other words, little m v prime is going to equal big M v. And you can do more steps to set that up, but you almost can see that equation just right there looking at the little diagram that I've drawn there. And very quickly, v prime pops out in terms of the other variables, constants, whatever we're calling them. I guess variables would be probably politically correct. All right, so that's what v prime is. We just plug that back into here, and that gives us our total kinetic energy, which is also the work done by the man, W. And so we just get this, and you just do the algebra as quickly as you can. Do it accurately, right? Squared, no, that's going to cancel. And you just group it together so it's going to look like something in one of your answers. I'm going to pull out the 1/2. I'm going to pull out the v squared. And that's going to give me a big M plus big M squared v squared over 1m. I think I've done that right, so let's check. Our answers. Okay, so the 1/2 and v squared is pulled out of those bottom three answers, and the parentheses is m plus m squared over m. So no, I didn't do that right because I need to pull the v squared out, of course. Screwed up my algebra there, so yeah, the v squared is out, and in the parentheses I have m plus big M squared. Big M plus big M squared over little m, which is answer D. And that's the one that I want. So again, that's the work done, is the total kinetic energy in the final situation. It's a pretty straightforward problem. It did take me a while to explain that, and I did kind of bobble some algebra there. But honestly, the first time I went through this, I smoked through this one pretty quick. I would categorize this as a pretty easy problem once you know what you're doing. So that's it. Number 65 off of the 96 exam. As always, thanks for watching. See ya.